Let's take a look at projectile motion worksheet number 2. We had questions 1, 2, and 3 last night. I want to take a look specifically at question number 3, which I think will pretty much cover everything that we had in previous questions as well. After we've gone over this, then we're going to give you one more question for you to work on at your desk just to kind of see how it's going, and then we'll kind of play it by ear to see if we need to do any more questions after that or not. Number 3 says, a punter in a football game kicks a high, booming kick from his own goal line. He kicks the ball at a 60-degree angle with a velocity of 25 meters per second. What's the hang time? How far downfield does it land? And I asked you one additional question. We called it 3C. That is, what's the maximum height of this football as it goes through the air? First thing we want to do for this is draw a picture. So listen, we're kicking it at 60 degrees, 25 meters per second. Let's label the 60 degrees down here with the ground, and the velocity or the speed right here at 25 meters per second. We know this ball is going to take a path that looks something like this. Can you tell me what the shape of that path is? Math people? Even physics people that have been paying attention for the last few days? What is it? It's a parabola, right? In fact, we know that the y component equation describes the equation for a parabola. We got a funny angle there. We don't like that, so we get rid of it off to the side over here. We got 60 degrees right here. We got a speed of 25 meters per second. Let's label a triangle, a right angle triangle, with an x and a y. Make sure that 60 degrees is inside it, right? Now, that 25 meters per second, is that the opposite, adjacent, or hypotenuse? Which side of the triangle is it? Opposite, adjacent, or hypotenuse? O, A, or... Which one is it? 25 meters per second.
That's the hypotenuse.
Yeah, it's the... Yeah, exactly. So if that's the hypotenuse, and x is the, what side is that? Opposite or adjacent? Adjacent. Adjacent and hypotenuse go with the cosine function. So we're going to say cosine 60 degrees is equal to x adjacent over 25. That ends up being equal to, I think, exactly 12.5 meters per second. Now we'll do the same thing almost with the y component. It's the opposite side of the triangle, so we're going to use sine for that. Sine is equal to opposite over hypotenuse. And this ends up being 21.6506 meters per second. We'll box it off there just so that we remember it's kind of off to the side there. Look, you're solving a projectile motion problem which is largely different than one of those adding vector problems. But in the end, we got a funny angle. And we know every time we see a funny angle, no matter what the context, even if it was Physics 30 next year, Unit 1, where you had a collision between two objects and you had to use a law called the law of conservation of momentum. If we had a funny angle, we'd still get rid of that funny angle, break it down into x components and y components, exactly like we have here. Now, the following is what makes this question a projectile motion question. Break it into x and y. Which equation do I use always to describe the x component? V equals d over t, because it travels at a constant velocity. In fact, at least it travels at a constant velocity horizontally. If I was to draw in the horizontal velocity right here, and I was to draw in the horizontal velocity right here, it would look exactly the same, because it isn't changing. The horizontal velocity remains the same over the entire trip. Does that make sense? Now, does the vertical velocity remain the same? No, so that means it's accelerating, which means I have to use one of the acceleration equations to describe the y component. Any of them are valid, but the one that's going to work the most often is which one? VI, not VI plus t, VI times t? Yeah, plus 1/2 AT squared. If you don't remember the exact form of the equation, that's okay, because you can always check your data sheet, right? You just have to kind of remember, you have to be able to recognize which equation it is. Now, this is an acceleration equation, but we also talked about how this really is the equation for a parabola, which describes the shape of this projectile. So it makes sense that that's the one that we're going to start with. Now, let's sub in some numbers here. What's the value of v for the x component? How much of that x component, how much of that 25 meters per second is horizontal? We just got rid of a funny angle because we didn't like the 25 meters per second, right? So we just got an x and a y. Maddie, what is it? 12.5. Yeah, it's 12.5 meters per second. So all we're going to do here is replace the 12.5, this 25 meters per second with the 12.5 meters per second. So instead of launching it at 25, we're pretending that we're launching it at 12.5, because that's how much of it we are launching it at horizontally. Then, of course, it remains that speed horizontally through the entire trip. We don't know what d is. How far does it travel horizontally? Don't know. Don't know what t is either. Do we know the displacement for the y direction? Where it ends relative to where it starts? Final position y minus initial position y. Ireland, do you know what that is? If it starts right here, it ends right here. Yeah, the horizontal displacement is not 0 because it moves downfield, right? But the vertical displacement is. And then, of course, one more that's different. One more that makes this different than those horizontally launched projectile motion problems. Read, what's the y component of the initial velocity here? Yeah, 21.6506. So let's fill that in now. And we're going to multiply that by the time plus 1/2 of neg 9.81 times the time squared. So what makes this question different than those questions where we just launched an object off the edge of a cliff horizontally like this? What makes it different? The things that are in color there. If we were launching it horizontally, whatever number we were given for the initial velocity, let's say 10 meters per second, would be the number that we would sub in for v, for the x component. What else is different? The y component. The initial velocity for the y component here would be 0. Here it's, well, whatever the y component of 25 was, 21.6506. And finally, the third difference is that in this one, the y displacement is negative of whatever the height is. So in this case, we would say negative 15 meters. But in this one, since we land at the same level as we start, the y displacement ends up being 0. Other than that, it's exactly the same. Of course, you're solving for different variables, and mathematically, the algebra works out to be a bit different. But physics-wise, thought-wise, it's the same except for these three colored numbers. All right. I see a time over here, and it's in two places, but there's only one variable. How do I solve for time on the right-hand side? How do I solve for that time on the right-hand side? Got to somehow get it in one place by itself to solve for it. Yeah? Yeah, let's divide everything by time. I can divide everything by 37.2 if I want, right? But it's not very helpful to divide everything by 37.2. But I could. It makes more sense to divide everything by time because you're going to end up canceling some things out when you do that. 0 divided by time is 0. T divided by, here, let's fill that in. T divided by t is 1. So it's 21 times 1. Half of neg 9.81 is neg 4.905. T squared divided by t is t. So I'm going to end up with 0 is equal to 21 minus 4.905 t. I want to take that 21 over to the other side because it's not touching or it's not connected to the t. How do I take it over? Yeah. Yeah, sometimes we think we add it because we see 21 minus 4.905. No, we take it over by minusing it because it's plus 21 minus 4.9. So if it's plus 21, we take it over by subtracting. We get negative 21.6506 equals negative 4.905. Now we're going to take 21 and divide it by 4.905. And we're going to get somewhere in the range of 4 meters per second, I think. Let's go with the unrounded number there, 4.41399. There we go. There's the time. We call that the hang time. And I think that's the first thing we were looking for, wasn't it, the hang time? So we'd round that actually as a final answer to 4.4 seconds. But since we're going to use that to find out how far downfield the ball ends up going, we want to also keep the unrounded number. Take this number, sub it in here, 12.5 times 4.41399, which is exactly what I got to do. gives me 55.17, or we'll say 55 meters. So the hang time, the time that the ball stays in the air, 4 seconds. I'm not a real big football guy, so I'm not sure if 4.4 seconds is good or not. Why would you sometimes want a bigger hang time? Yeah, it gives you more time to catch up, more time to go downfield, right? What would be the disadvantage of hang time sometimes? The disadvantage of hang time would be that the ball doesn't necessarily go as far, right? You can make it like 25 seconds hang time if you can kick the ball hard enough. Okay? But unless you're going to either kick the ball right off the field or kick it almost straight up, then you're probably not going to have 25 seconds hang time, right? Bottom line is it's that balance between how far the ball goes and the hang time, which sometimes you got to sacrifice one. Okay, so there we go. What if we want to find the max height here? In other words, we want to find this value right here. What variable do you think we're solving for there? Taylor, what do you think we're solving for there? Not h. We're not going to call it h when we're solving for it, right? But yeah, it's displacement. Is it horizontal displacement? Brogan, is it horizontal displacement or is it vertical displacement?
Vertical.
Good. It's vertical displacement, so we're going to analyze the y component, but we're going to analyze it halfway in, right? To find the max height, I'm going to say that Vf squared is equal to Vi squared plus 2AD. And I'm going to solve for D. So let's get rid of the Vi first, because it's not attached to the D. Vf squared minus Vi squared equals 2AD. And then let's take the 2a over by dividing. Vf squared minus Vi squared over 2a equals D. What's Vf? Horizontally, the speed doesn't change, right? If it was, what was it, 12.5 meters per second, it remains 12.5 meters per second through the whole trip. But vertically, it started off as, what, 21 meters per second? And then it slowed down vertically until eventually it stopped. When does it stop? At its max height. So we're going to say when we're analyzing the max height, Vf is 0. Vi is 21.6506, the initial y velocity, times 2, or divided by 2 times negative 9.81 meters per second squared. So we're going to say 0 squared minus 21.6506 squared. And let's divide that by, use some brackets on the bottom, 2 times negative 9.81, all inside one set of brackets there, gives us a value of 23.9 meters, or 24 meters. How high does this ball go in the air? 24 meters. We have just successfully solved essentially what boils down to question number 1 on your final exam. Different context, different numbers, but if you can solve this question, you can solve question number 1 on your final exam. In addition, if you can solve this question, you can solve the question on tomorrow's quiz as well, which will be essentially the same as this as well.
How many questions are in the final exam?
10 multiple choice, something like 12 written questions like this. So you got to figure if you can solve this, you're probably at like 7 or 8% on your final exam right now. It's a good start. I hope we get a few more points beyond that. Okay, but at least it's something to start with.